Now we have the presentation of Dr. De Rosa. Dr. De Rosa is a researcher at the University of Naples Federico II, and he stayed around the world, sometime in France, and also he got sorry, and his scientific activities focus on the design and development of nano and micro-size delivery system for peptide, oligonucleotide, and anti-cancer drugs. And in 206 and 2000, he was a coordinator of a European scientific project, International Program Galileo, and now a project supported by the Minister of Salute. Professor Dr. De Rosa.
Problem with the presentation, I don't know why.
I forgot the title of the presentation. Dr. De Rosa will present a study on liposome encapsulation zoledronic acid, a new opportunity against cancer.
Only one moment, there is a problem. I can take another break.
So.
Se non la versione originale.
Okay.
Okay, sorry for technical problem. And thank you for the introduction an hour ago. And I'd like you also to thank you, the organizing committee, to give me this opportunity, especially in my case, because this presentation at the moment had not data on brain targeting, but only on cancer targeting, and the brain targeting will be, I hope, the next step. So, zoledronic acid. What is zoledronic acid? Is a third generation biphosphonate able to inhibit bone resorption. Bisphosphonate had analog of ATP, non-hydrolyzable analog of ATP, and for example, zoledronic acid is also present into a marketed product, Zometa and Aclastad, and for the bone resorption activity, for inhibition of bone resorption activity, these drugs are currently used in the treatment of bone metastasis and osteoporosis or Paget disease. The mechanism is due to the fact that this drug concentrates into the bone close to the osteoclast, inhibiting formation, differentiation, and activation of osteoclast, and then favoring their apoptosis. So the results is the inhibition of bone resorption, very useful, for example, in metastasis, in bone metastasis. But zoledronic acid is also a very interesting molecule because it's possible to induce apoptosis in a number of cancer cells, for example, cancer cell of multiple myeloma, breast cancer cell, prostate cancer, and so on. And for these, many authors hypothesize that the beneficial effect of zoledronic acid on the metastatic bone tumors could also result from a direct anti-cancer activity, and so this activity could also be useful in the treatment of other tumors different than bone metastasis. But the problem is the pharmacokinetic profile of this drug, because zoledronic acid is generally is injected by infusion, slow infusion, but rapidly accumulate into the bone. About 55% of the drug is concentrated into the bone. And so this is the cause of the side effects, so osteonecrosis of the jaw, and moreover, it's very difficult to attain high concentration of the drug in other side of the body, so at tumoricidal concentration. So our strategy in this work was to develop a carrier able to deliver zoledronic acid into tumors, and the aim was to reduce zoledronic uptake into the bone and also to increase a concentration of the drug, for example, in other tumor sites. And so we choose the more classic carrier, type of carrier, pegylated liposome, long circulated liposome, with all the advantages that I think every one of you know, and comprising a passive targeting due to APR effect. And this is the outline of the work. And of course, we concentrate on the second part, on the development of the formulation encapsulating zoledronic acid, and this is a schematic representation of our work, in which we developed the two formulations with a different amount of PEG on surface. And then I have to say that zoledronic acid is a molecule, hydrophilic molecule, but with a low water solubility, so it's very difficult to have high encapsulation efficiency. And so to avoid this problem, we check the possibility to encapsulate the molecule with, for example, different additive in the aqueous phase. Then we use different preparation methods that are summarized here. Then also different purification methods. And we also tried to use lyophilization in order to have a long storage of the formulation. So we selected a reverse phase evaporation technique after purification. Liposome were also lyophilized, so we obtained a powder able to be reconstituted rapidly with water. And these are the characteristics of liposomes that we obtained. And so the next step has been the in vitro studies of the formulation. In the first time, we try to understand something concerning the intracellular distribution of the formulation and then in vitro activity. Concerning the intracellular distribution, we had a problem in this case because zoledronic acid is a very small molecule. The producer hasn't the radiolabeled zoledronic acid, and its modification of, with, for example, a fluorescent dye, it's not possible without altering the characteristic of the drug, so it's impossible to follow down the dye. So we used, in this case, only a co-encapsulation. We co-encapsulated liposome with another dye and to follow the intracellular distribution of the liposome. Of course, these data that I show here are all indicative, so we obtained a strong fluorescence, I don't know if penetration, I hope, into the cytoplasm. And so the following step was to confirm this result by the activity of these the zoledronic acid encapsulating into these liposomes, and in particular we started with prostate cancer cells and PC3, and we found that our formulation were not toxic on the cell growth. On the contrary, zoledronic acid, according to the literature, was toxic depending on the concentration, but the surprise was that our formulation was more toxic than zoledronic acid, so we obtained an amplification of the effect. This was a surprise because the aim was only to change distribution into the body, not intracellular distribution. And these data were also confirmed with another cell line of prostate cancer. And then we tried on, for example, a cell of multiple myeloma, in this case doxorubicin resistant. We obtained the same results. And then we checked other kind of cells. In the majority of the case, we obtained that the cell viability, the reduction of cell viability obtained with zoledronic acid was increased with the two formulations. And then the next step has been to test the activity in vivo. And in particular, we selected two tumor model, multiple myeloma and prostate cancer. So in the first model, we used the model in which multiple myeloma cells are injected into, subcutaneously injected in mice, and after tumor growth, there is the administration of the formulation, in this case in a weekly injected dosage. And the experiment give these results shown here. So this is the control, okay, this is tumor volume, and this is liposomes alone. This is the effect of zoledronic acid, and this is the effect of zoledronic acid encapsulated into the liposomes. So we obtained also in this case, we confirmed also in vivo an amplification of the effect of zoledronic acid, and this is also evident, more evident with the survival that was significantly improved by use of this formulation compared with Zometa, that is the drug currently used in bone metastasis. And then we started with another in vivo model, in this case a model of prostate cancer, in which we injected the mouse with PC3 cells, and in this case we injected after tumor growth two dose of zoledronic acid, and in this case, we obtained these results shown here. In particular, this is the control. This is a blank liposome. These are two formulation, concentration of zoledronic acid alone. And as you can see, we obtained a strong difference with our formulation. In this case, for example, we obtained almost a total reduction of tumor growth. And of course, it was also surprising for us. So at the moment, we can conclude that we obtained two formulation, freeze-dried formulation of liposome containing zoledronic acid, and this formulation show an inhibition of cell growth enhanced with liposome zoledronic acid is used compared with the free drug. And moreover, this formulation induced inhibition of tumor growth and survival on different animal model of tumor, in particular multiple myeloma and prostate cancer. And at the moment, the perspective of course, to organize also clinical studies, but this is very difficult, and we are also looking for financial support for this. And moreover, we are also improving the formulation. For example, we have developed nanocomplexes containing zoledronic acid, and we have promising results, but only preliminary on cells. Moreover, we are modifying the formulation in order to obtain an active targeting in prostate cancer. And the next step, this is also the reason for my participation here, is I'd like to modify this liposome in order to obtain also brain tumor, because zoledronic acid also showed in preliminary result promising activity, in cytotoxic activity on cell on neuroblastoma. And so I'd like also only to thank you all people that contributed to this work. So my group on Naples, Professor La Rotonda and Dr. Giuseppina Salzano, and then all the group of the Seconda Università di Napoli with Michele Caraglia, Monica Mara and Alberto Abruzzese. We working in close contact all time in this project, and then the group of Catanzaro with the Professor Tassone and Professor Tagliaferri for the experiment in vivo on multiple myeloma, and last but not least Dr. Carlo Leonetti for the excellent experiment on prostate cancer, and thank you for the attention.
Thank you, Dr. De Rosa. Now the session is open for questions. There are any questions?
Thank you. If you propose to use this liposomal formulation for brain tumor therapy, do you expect that the liposome will migrate through the BBB as they are, or do you think they will simply fuse with the endothelial cells and then they release the Because most of the cases that we have seen in the last 2 days are done considering solid microparticles. Liposomes are not solid, and what do you expect?
Well, I think that the only way is to test. So, of course, we have to functionalize this liposome. So we could start, for example, with this formulation. I don't know if we can have results. So, but of course, we have also intention to work on the formulation. We are in order to improve brain targeting or passage through brain BBB.
Any question? I have some questions. First of all, probably I missed it, but which kind of cryoprotectant did you use?
Lactose. We tested different cryoprotectants.
And all the experiments in vitro and in vivo were made after freeze drying?
Yeah.
Did you check the same activity before and after freeze drying?
Not the well, at the beginning we started to test the in vitro activity with not lyophilized liposome, but after all the experiments have been performed with lyophilized power, because we think to something that could be useful, for example, for a patient. So liposome, in this case we used a particular formulation I missed by, for example, I used a basic pH inside liposome to have an encapsulation efficiency. Mm-hmm. So liposome cannot be stable in this form, so of course I have to lyophilize, and so it's necessary to test the formulation after reconstitution with water.
With water. And did you check also the percentage of the drug concentration, the leakage of drug, also after
yes.
Resuspension? Or
this is a very good point, because this was one of the problem during the work of formulation, and this is the reason for that. Also, we used only one formulation in the animal model, in vivo model, because there is one formulation with the higher amount of PEG and the higher amount of diasteroyl phosphatidylethylamine that have the lower leakage. There is only less than 10%, 20% of the leakage, so we use only this formulation. The other one had some problem.
Okay. Yeah.
Regarding the active targeting, which kind of ligand do you think to use for the prostate cancer?
At the moment, yes, at the moment we are working on a patented peptide, and that is an agonist of receptor rutensin, and there is a peptide that has been a cyclic peptide, so a particular peptide has been patented by the group which we are collaborating this moment, and so we have already put it on the surface of lab, and we are testing.
And you have an idea of which kind of linkage you will use between the ligand and the PEG terminal part of your liposome?
What kind of bound or spacer?
Yes, both of them.
Wait, the spacer is PEG.
Yes,
and
after the PEG.
Malinimide.
So you will evaluate
I don't remember, but no, it's an extra, I think. So, for example, there is, if I remember the synthesis work, there is the treatment of the peptide, of the amide part of the peptide with the trout reactive in order to add a cysteatiolate. Okay. And after there is a reaction with the malinimide.
In the PEG?
Yeah.
Okay, thank you.
Thank you.
Any more questions? No. So I close the session for questions, and